Okay, everyone, it's our last hurrah. So today we're going to finish up 8-7, and then the final is Monday, as you know, from 11 to 1:45. I was thinking, man, that really sucks because Sunday is Mother's Day. I was thinking about doing a like a study session or something where I could become available to have everyone kind of come into a Zoom session to ask questions and go through problems. I was thinking about doing that on Sunday, but we're going to be hosting Mother's Day, so I don't think I can do it. But maybe Saturday, I don't know. I'm thinking about sending it. I would send it out to your class and then my Cal 1 class as well. I'm going to see if Saturday I can fit maybe like a 3-hour window in where I can be available. But just pay attention to your email. And if you have any questions, over the weekend, please just contact me via text, or call me or something if you have any questions. Okay, so let's get into the 8.7. We didn't quite finish it last time. We established, I guess, a formula for figuring out what the Taylor series or Maclaurin series is for a function. And it required that we be able to take successive derivatives of the function and try and either find a pattern and establish a formula, or write out each of the terms. And then after we write out the terms, establish a formula. So there's kind of like two different ways to go about it. So I want to make sure that I illustrate that today with some examples. The notes, what we had done, we had established what the Maclaurin series was for e to the x, right? We did that. And then the next example said for us to use the answer that we just did for example 1 to find a new expression for e. So I want to just do this because it's not going to take us long. What we established last time was that e to the x is equal to the sum n equals 0 to infinity of, anyone remember? It was 1 over n factorial x to the n, right? That should be in our notes from last time. It's one of the first examples we did, right? Where is it? There it is. Okay, so is this right here? We did that last time. So we know that that is the Maclaurin series for e to the x. If we write out the terms, plugging in, 0, then 1, then 2, we get 1 plus x squared over 2 plus x cubed over 3 factorial. These are factorials here, but 2 factorial is 2, so that's why I just left it. And it keeps on going forever and ever, right? So if what I'm saying is, can we find a new expression for e? Like e to the first power, right? That's what e is. Well, if we just replace all the x's, right, with 1s, then we have a new expression for e. It'd be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial forever and ever. Or if you want, you can put these two together. It's 2 plus those things, right? So if you get on your calculator and you do 2 plus 1 over 2 plus 1 over 3 factorial, which is 1 over 6, right? If you were to do that on your calculator, 4 factorial is 24. If you were to continue to do this and start adding these up on your calculator, it would get closer and closer to the value of e, which is 2.718, right? So it's an equivalent expression, right? E can be written as that infinite series. All right, that was just to demonstrate another way you can look at the number e. Okay, so we covered that. We did not do example 3, but we did example 4. We found the Maclaurin series for sine, and we found the Maclaurin series for cosine. So in your formula sheets, in Canvas under Files, you will find a page called the Maclaurin series table, and it looks like this. All right, let me make this a little smaller so you can see it all. Okay, this you're allowed to have on your exam. All right. So the series that we have established up to this point this very first one was the pivotal one we needed for 8.6 when we were trying to look at how you rewrite 1 over 1 minus u, and we use this geometric series to do that. So that we've already established. E to the x we did last class. That's the Maclaurin series for that. Sine x we did last class. And I had pointed out that notice that all of the powers here are odd, right? They're all odd. And that's why we call sine an odd function. We established the power series for cosine, okay? And in 8.6, we actually established the series for natural log of 1 plus x. Go back and look at your notes from April 27th, I believe. Where is it? Right here. We expressed this as a power series, and we had gone through it, and we established the power series right here. We didn't know at that time that that was the Maclaurin series, but it is the Maclaurin series. So we have established all of those off of that table. The only two left are these two, which I'm going to do today. I'm going to make sure we understand where these come from. Arctangent's going to be kind of interesting. This one is going to be really interesting, but we'll get to that in a minute. All right. So sine, cosine, this one. Okay, so let's do this one. Let's do example 6 first. All right. We want to find the Maclaurin series for this. For x squared cosine of x, right? So if we go through and do what we did last class, what we would do is we would start making kind of like a table of derivatives, right? So we have the derivative here, and then whatever the function is going to turn into. So the 0th derivative would be x squared cosine x. And then the first derivative, see, this is going to suck, isn't it? Because when we take the derivative of that, it's going to be product rule. Right, we have a product rule there. So we would have 2x cosine x plus the derivative cosine, which is negative sine of x, and then times x squared, which I could write as 2x cosine x minus x squared sine x. That's our first derivative. And do you see how quickly this gets bad? Right? When I do the second derivative, I'm going to have 2 product rules in here. This looks horrible, right? This looks horrible. I do not want to have to do this. But I already have established what the power series for cosine is, right? I've already established that. So instead of doing this method, right, what we're going to do is we're going to use what we know about cosine to establish the power series, the Maclaurin series. So I'm going to rewrite this as x squared times, well, cosine we said was the sum, right? And we can just go to this power series right here, which is from our notes last class, right? I'm just going to use that Maclaurin series. So we've got sum n equals 0 to infinity, -1 to the n times x to the 2n over, over 2n, right? That's our Maclaurin for cosine. So all I have to do now is push the x squared into the sum, and when it goes into the sum, it's going to sit right here next to the x to the 2n. And I can just use properties of exponents to add those exponents, add the 2 exponents up, right? Which gives us sum n equals 0 to infinity, -1 to the n times x to the 2n plus 2 all over 2n. Oh, did I forget my factorial on the bottom? I apologize. Right, 2n factorial. I forgot my factorial. Yeah, oh my gosh. 2n factorial on the bottom. And that's it. Okay, that's it. I'm done. I have the Maclaurin series for x squared cosine x. That's nice, right? I used what I knew about cosine to create the Maclaurin for this. On your exam, I will be very clear about whether or not I need you to do this to get the Maclaurin series, or if you can not cheat, but use what you already know to create the Maclaurin series. So like on the review, where's my review? I had them all ready here to go. Where are they? This damn thing. Oh yeah, there it is. So like on the review that I sent out, number 7, find the Maclaurin series for e to the negative 2x. You must derive the series and may not use the table. The table meaning this, you can't use that, all right? You have to do it by hand. Same with number 8, find the Taylor series for this about a equals 2. You must derive the series, can't use a table. Now, after that, you can, if I don't tell you, right? If I don't tell you, hey, you can't use the table, then you can use the table. So like for number 9, I'm allowed to use the table. For number 10, I can use the table, all right? If I explicitly say you must derive it, then you have to do it like we did last class. Is that clear to everyone? Sure. So in this problem, I did not say you must derive it. So I just used the table and got the answer. Okay, so that takes care of example 6. Let's go back to example 3. And let's find the Taylor series for e to the x at a equals 2. So this is a Taylor series, not Maclaurin series, right? So that means that my center is at 2, not at 0. So I'm going to have to derive this, all right? So I'm going to make a table here. This is going to be my derivative. This is going to be the function. So the 0th derivative is e to the x. The first derivative is e to the x. This was the nice one, right? E to the x again, right? And this just keeps going. So if I take the nth derivative, I get e to the x. So what I need to do now is I need to evaluate these at 2. So I'm going to take each of these and replace the x with 2. So e squared, right? E squared, all the way down to e squared. So I have a formula, right, for the nth derivative, right? This right here is the nth derivative of the function at a, or if you want, you could say the nth derivative at 2, right? Now, what I'm now going to use is the generic formula for a Taylor series. Taylor series in general, just look at your notes from last time, or I'll bring it up so you can see it. Taylor series right here. This is what the Taylor series looks like. I'll copy it. Slap it in here. I really only need this first part right here. So I'm just going to use this right here. All right. Oh, and I need to tell you what the C sub n is. Oops, I grabbed the wrong one. Apologize. Right here. Let me just grab this one. Here's your Taylor with that formula right there. So we're going to do this sum right here. Okay, we're going to write this out, and we're going to start at 0, go to infinity. And now the big question is, do we have a formula for the nth derivative at a? And yes, we do, right? It's this. It's e squared. So that's just going to become e squared right there, right? That's this. And then over n factorial. And then we have x minus a, but a is 2 here for us, so 2 to the n. That is our Taylor series. It's nice to do e to the x, right? Because e to the x, when you take the derivative over and over, it's itself. And that means you'll have a formula for this. Questions?
Sir, I can't remember from last lecture. Didn't you say, I wrote it in my notes, I may have written differently then. Wasn't the Taylor series n starts at 1 instead of 0? I thought.
No, not for Taylor. The only time we're gonna get 1 is if we have a power series and we take its derivative. Then the index shifts up to 1.
Okay, gotcha. I just wrote my notes wrong.
Okay. Any other questions? Okay, so we have the series. All right, let's do the one that we haven't looked at. This one right here, arctangent. I want us to establish this series. All right. This is a good exercise. So let's try and prove that this is the Maclaurin series, right, for arctangent of x. So we can't use the table. I mean, the table has the answer, okay? We're trying to prove that this is true, all right? So what we're gonna have to do is treat this like our function, f of x, right? And then try and see what this is gonna look like if we start to make our table. And we're trying Maclaurin here, okay? All right, Maclaurin, which means a is 0, right? So there's our derivative. Our 0th derivative is inverse tangent of x. Our first derivative, well, the derivative of arctangent is 1 over 1 plus x squared, right? But see, the second derivative, this is going to start to suck pretty bad, isn't it? Because, I mean, we'd have to rewrite this as 1 plus x squared to the -1. So when we take the derivative again, it would be -1 plus x squared to the -2 times 2x, chain rule, right? See how bad this is going to be? Especially on the next derivative, it's going to be really bad. So I start to question whether or not this is the correct approach, right? I mean, I told you last time, 8.7, we have a formula. We have a way of getting a series, a Maclaurin series, as long as we can take derivatives. But see, this is an example where the derivative just continues to get worse and worse and worse. So even though we have the formula, the work required to get the derivatives looks kind of too challenging. Do y'all agree with that? This just looks like it's going to be a mess. Imagine the 5th derivative of this. I mean, just crazy, right? So the way I'm going to approach this is actually using not the stuff we learned in 8.7, but the stuff we learned in 8.6. Because inverse tangent of x, right? I know that the derivative of it, right? The derivative of it is 1 over 1 plus x squared. But this looks a lot like 1 over 1 minus u, right? That generic formula that we had for a power series. I could rewrite this as 1 over 1 minus -x squared. And then I can use the series for 1 over 1 minus u and rewrite this, right? This would become sum n equals 0 to infinity of -x squared to the n. You all right with that? And that is equal to, let me just clean it up a little bit. I'm going to take that -1 out, -1 to the n times x to the x squared to the n, which is x to the 2n. So this is what the series is for the derivative of arctangent would be this series, right? That's what the derivative would be. That's not what we want though. We want the actual series of arctan, not its derivative. So what can I do?
We integrate that.
Yeah, just integrate. If we integrate this and integrate this, this right here will go back to the inverse tangent function. And then this side, well, we have to do the antiderivative of this. And when you do the antiderivative of a power series like this, we can use the power rule, which means this will go sum, and we're doing antiderivative, so the index does not shift up to 1, it stays at 0. And now here comes the power rule, 1 over 2n plus 1 x to the 2n plus 1. So all I'm doing is adding 1 to the power and dividing through by 1 more than the power. That should be our power series for arctangent. So notice the integral sign went away, right? I took the antiderivative, so I applied the power rule. Does that match the formula? Let's see. Where is it? That's it, right? That's it right there. Now, I want to show you something slightly different, just a little bit different. This step right here, when I was here, I want to show you a different way of doing the same thing where you don't use the power rule, you write out the terms, because you should see both ways and be comfortable with both. So when I'm here, right? When I'm here and I'm like, okay, I need to take the antiderivative, this side will be inverse tangent of x. This side, before I take the antiderivative, I'm going to start writing out the terms. Okay, let me write out all these terms. So if n is 0, I get 1. Then if n is 1, I get a negative, and then I get x squared. And then if n is 2, I'm going to get a positive, and then x to the 4th, then a negative x to the 6th, then a positive x to the 8th, negative x to the 10th, plus dot, 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 right? dx. That's what I'm trying to do, is find the antiderivative of this. So do you see I'm not going to use the power rule. I'm actually going to integrate each of these term by term. This will give me, what, x minus 1/3 x cubed plus 1/4 x, I just, 1/5, sorry, 1/5 x to the 5th minus 1/7 x to the 7th plus dot, dot, dot. We understand the pattern there? Now, from here, this is correct, but now I could go back to a series. I have to see the pattern though. So I look at this and I say, okay, it's alternating, starting with a positive. So I'm going to go -1 to the n. And then what I have, there's x to the 1st power, x cubed, x to the 5th, x to the 7th. Those are all odd numbers, right? Starting with 1. So I'm going to go x to the 2n plus 1. Now remember, n starts at 0. That's why I did 2n plus 1. Because when I plug in 0, I get 1. When I plug in 1, I get 3. Plug in 2, I get 5, right? And then I want to divide all that by the same numbers, 1, 3, 5, 7. So I put 2n plus 1 here. And that exactly matches what we got there. You should be comfortable doing it both ways, all right? Questions there? All right. Where's my sheet? One more off this table that I want to show you. And this one is a little tricky, very tricky, all right? Confusing. So before,
K over N?
It's K, yeah, that's what I'm going to start with. I want to start with this, but all right. So there is a mathematical notation, K on top of N inside of a set of parentheses like this. I'll tell you what it's called in a second, but let me tell you what the definition of this is. This means K factorial over N factorial, and then N minus K, wait, hold on, sorry, K minus N factorial. That's what that means. So for example, if I write 5 on top of 3 like that in parentheses, what it means is 5 factorial over 3 factorial 5 minus 3 factorial. Let's just figure out what this would be. This is 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. Right, so 5 factorial is that, 3 factorial is this, 5 minus 3 is 2, right? 2 factorial is 2 times 1. Understand? So this just turns out to be, let's see, 3 times 2 times 1, that's all gone. And then I get on top 20, 5 times 4. On the bottom, I get 2. So this is 10. All right. Let me give you another one. What if I do that? This will be 3 times, let me write it out first. This will be 3 factorial over 2 factorial, 3 minus 2 factorial. So 3 factorial is 3 times 2 times 1 over 2 times 1, and then 1 factorial. The 2 times 1 cancels, and you just get 3 over 1, which is 3. So
This is a weird operation.
It is a weird operation. Let me explain what it is. All right, let me explain what it is. So right here on this first one, the 3 means, let's say we have 3 objects. Okay, let's say we have 3 objects. One, let's call it object A, object B, and object C. All right, I have 3 things, 3 people lined up against a wall, whatever you want. Okay, 3 objects. And what I want to do is I want to choose 2 of them. Okay, I want to choose 2 of them. That's the second number. So I could choose 2 this way. I could do A, B, right? Right, that's one way I could do it. I could do A and C, right? And what else could I do?
B and C.
B and C. Is there any other way I could take 2 from that group of 3? No, right? I'm either going to have A and B, or I'm going to have A and C, or I'm going to have B and C. There are only 3 ways to choose 2 objects from a group of 3. And that's what this number represents, is how many ways you can choose 2 things from a group of 3. Here, this is 5 objects, and you're choosing 3 of them. So if I have object A, B, C, D, and E, right? I have those objects, and that's 5 things, right? And I want to choose 3 of them. There's 10 ways to do it. Should we try it? It's going to suck. A and B, A and C, A and D, A and E, right? That's A with all of those, right? How about B? We could do B. Can we do B and A? Well, we already have B and A, right? But we could do B and C. We don't have B and C yet, do we? We could do B and D. We could do B and E, right? All right, how about C? Can we do C and A? No, we already have C and A. Can we do C and B? No, we already have C and B. Can we do C and D? Yeah, we don't have that anywhere. How about C and E? Yes, right? You following me here? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only one more possibility here. What's the other possibility?
B, D, and E.
D and E. Am I missing anything?
Aren't we picking 3 objects?
Oh, wait, am I picking? Oh, shit. Sorry, this was, I messed up. It's 3 things. I should have said something earlier. Sorry, I was doing 3. Okay, so hold on. I am missing something. Hold on. Let's stick with this. Let's stick with this. Let's see. C and E. How about D and E, right? That was the only one. Is there any others? Am I missing any others? I don't see any others that I'm missing. D, I think I've got them all. So let's see, there are 10 things here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But this is what 5 choose 2 should be. Let's check it. 5 factorial over 2 factorial, and then we do 5 minus 2 factorial. So this is 5 times 4 times 3 times 2 times 1 over 2 times 1 times, let's see, 5 minus 2 is 3. 3 times 2 times 1. I'll cancel those. And I still get 20 over 2. It's 10. Sorry about that. Can you imagine? Okay, can you imagine that picking 3 now? I mean, that's tough, right? I mean, like you have to get all these combinations and stuff. Or imagine I give you 100 objects and I tell you to pick 13 of them. How many ways can you do that? That's hard. It's easy when it's like 3 objects, pick 2. There's only so many scenarios and you can do those mentally. But if there's 100 objects and you have to take 17 of them, no one's going to be able to tell me how many ways that can be done. So anyway, this notation right here, this notation means this, okay? This is called, hold on. This would be called K choose N. K choose N. So you have 5 objects, choose 3. 3 choose 2. 5 choose 2. That's the way you'd read this. This is used in probability and statistics. That's where you see this. All right. All right. Now let's get to what we want to get to. What we're trying to do is find the Maclaurin for the function f of x equals 1 plus x raised to the k power. All right, we are going to have to create the table. We're going to take our derivatives over here, and this will be our functions. So if I don't take the derivative, right, I'm going to just have 1 plus x to the k, right? If I take the first derivative, I use power rule. K comes down, 1 plus x to the k minus 1 times the derivative of what's inside. The derivative of what's inside is 1. So that's all I get for the first derivative. Second derivative, this k minus 1 comes down and joins the k. So I'm going to have k times k minus 1, 1 plus x. Now I subtract 1 again, so k minus 2. And then I take the third derivative, k minus 1. Now the k minus 2 comes down, and then I have 1 plus x to the k minus 3. Everyone understands that k here is a constant, right? That's why when I'm taking these derivatives, I'm not having to use product rule. Everything I have here in yellow, these are all just constants. So there's no product rule when I take derivatives. Y'all following this? Can you tell me what the nth one would be? Maybe I'll do one more before we do that. Let's see, the fourth one would be k minus 1, k minus 2, and I stop at k minus 3, right? On the fourth derivative, I'm stopping at k minus 3. On the fourth derivative, I'm stopping at k minus 3. On the third derivative, I'm stopping at k minus 2. On the second derivative, I'm stopping at k minus 1. And then I have 1 plus x to the k minus 4 now, right? So what would the nth derivative be? K minus 1, k minus 2. I would keep going until I get to where?
K minus n plus 1.
K minus, okay, and this number here, here is always 1 less than n, right? 1 less than n. So I am subtracting from this n take away 1, right? Does that formula work? If this is a 4, this would be k minus what? 3, right? If this was a 3, this would be k minus 2. Understand? 1 plus x to what power? K minus, and this number up here, 4, 3, 2, 1, is the derivative we're at, right? So this should just be k minus n. Now, I think what Hunter was saying, I believe you were right, Hunter, when you said this.
I was just distributing that negative across.
That's right. If you distribute this minus through, you get minus n plus 1, which is the same exact thing. So you could use that instead. Just distribute the negative. Okay. Here's our list of derivatives. We want Maclaurin though, right? We want Maclaurin. Maclaurin means that A is 0. A is 0. So that means we're going to go into each of these. Whoa. We're going to go to each of these and we're going to replace x with 0. So if I replace x with 0, then I get what here? Just 1, right? 1 to the k. So that's just 1. If I replace x with 0 here, I get k times 1 to any powers 1. So this is just going to be k. And then this right here, if I replace x with 0, you get a 1 here. So basically what I'm saying is that all of these become 1s when we do Maclaurin, right? So all you're left with are these things out in front. So next one will be k times k minus 1. The next one will be k times k minus 1 times k minus 2. And then k times k minus 1 times k minus 2 times k minus 3. And if we keep this pattern up, the last one will be k minus 1, k minus 2, all the way until we get down to k minus n plus 1. All right. So now I'm going to go back to what a Maclaurin series was. Where's our Maclaurin? Where's Maclaurin? Maclaurin right here. This is what a Maclaurin series looks like. And what I'm going to do is I am going to, instead of trying to take, well, let's do it 2 ways. Let's go first to this. Okay, let's go into that. This would be sum n equals 0 to infinity. And now I need to know what the nth derivative at 0 was. Well, that's this right here, isn't it? That's the nth derivative at 0. That's the nth derivative with us plugging in 0 because we're talking about Maclaurin. So that goes on top there. K minus 1, k minus 2, ... to k minus n plus 1. All of that divided by n factorial. And then x to the nth power. That is our Maclaurin series for 1 plus x to the k, right? That's the Maclaurin series. Let's write it out though. Let's actually write it out. I'm going to use this now, and let me do this in a different color. Now let's do it written this way, okay? So that's equal to f of 0. That just means this function right here with 0 plugged in, which gave us 1, right? That'd be our first one. Plus, all right, what was the first derivative at 0? Divided by 1 factorial. Well, here's our first derivative at 0. It was k, wasn't it? So I'm going to put k K on top, right? 1 factorial on the bottom, 1 factorial is 1, and then times X. Plus, okay, now the second derivative at 0. Well, here's our second derivative at 0. It's K times K minus 1. K times K minus 1 over 2 factorial plus, okay, now the third derivative, right? The third
Don't forget your
derivative.
X on that one.
Oh, I forgot the X. Yes, thank you. X squared. Plus, now the third derivative at 0, that's this right here. K times K minus 1 times K minus 2 over 3 factorial X cubed plus dot, dot, dot. That keeps going, right? You okay with that? That's the Maclaurin series. Let's double check it with the table. I want you to focus on this right now. Did we get this? Is that what we had? Yes. But we didn't get this. This has that weird notation, K choose N, right? K choose N is here. Instead of, what did we have? We had this there, right? This is what we had. But in the formula sheet, they're saying that this is K choose N. Is it? Is that what that is? I don't know. Let's see if it is. What does K choose N really mean? It means K factorial over N factorial times K minus N factorial. Do you all agree that's the definition? That's what I told you the definition was. Is this equal to that? Maybe. Let's see. Isn't K factorial K times K minus 1 times K minus 2, and that keeps going down all the way until I get to 1. Now I put it way out here for a reason. Do you all agree with that? That's what K factorial is on top. Over, okay, bottom left corner, N factorial. I'm just going to leave it as N factorial. But K minus N factorial, do you agree that what's here in this right here, do you agree that that is K minus N times K minus N take 1 away times K minus N take 2 away times K minus N take 3 away, all the way until I get down to 1? Isn't that what that means? To say K minus N factorial, you take K minus N, then take 1 away from that, take 1, and multiply these all together? Well, look, somewhere in here is K minus N. Somewhere in there, K minus N is in there, right? And then the rest of them down should cancel with these on the bottom, shouldn't they? What would be the one right before this one, though? The one right before this one would be the K minus N, but
Plus
shouldn't
1.
it be one more than this? Like not taking, because as we move to the right, you take away 1. So as you move to the left, you add 1. So that one's right in front of it. And if you see that, then this goes, this goes, this goes, everything here goes. And all you're left with is this. And that's what we had. In other words, a condensed, clean way of writing this is this. It's hard to see it. I mean, you would never like see that initially by yourself. You have to see it derived, but that's the easy formula for it. Now, let me show you this, okay? This is gonna maybe blow you away. I don't know, hopefully it will blow you away a little bit. We have now established the table, okay? We have everything now, right? So we know the Maclaurin series from 1 plus x to the k. So check this out, this is pretty cool. What if I asked you right now, what's x plus 1 to the third power? I think everyone in here could do this by hand, right? They could do x plus 1 times x plus 1 times x plus 1, right? And then you'd FOIL things out. And if you did this, you would get x cubed plus 3x squared plus 3x plus 1. That's what you would get if you FOILed that out. Okay? You believe that? You agree with that? Yeah. Okay. But this is actually the sum n equals 0 to infinity of 3 choose n x to the n. Why? Well, because that's what we just established, right? We just established that, where the hell is it? We just established this, that if you give me 1 plus x, or you could switch the order here, x plus 1 to the kth power, it should be this sum, right? This infinite sum. Let's try writing out this infinite sum. Start out with n being 0. And you know what? Yeah, let's just let n be 0. So if n is 0, you get 3 choose 0 x to the 0 plus 3 choose 1 x to the 1 plus 3 choose 2 x squared plus 3 choose 3. I'm going to get rid of this. X cubed plus 3 choose 4 x to the 4th. I'm going to do one more. 3 choose 5 x to the 5th. Now, plus dot, dot, dot. How about this? Everything from here down are zeros, because if I give you 3 objects and ask you to choose 4, there's no way to do that, right? If I give you 3 objects, tell you to choose 5, there's no way to do that. There's 0 possibilities. So everything from here on down is gone. It's zeroed. So that means the only thing left are these, right? So now let's do this. This, by definition, is 3 factorial over 0 factorial, and then 3 minus 0 factorial x to the 0. I know that looks crazy. Plus now 3 factorial over 1 factorial 3 minus 1 factorial x, and then 3 factorial over 2 factorial 3 minus 2 factorial x squared, and then 3 factorial over 3 factorial times 0 factorial x cubed, which is, let's see, what is this first one? What's 3 factorial over 0 factorial times 3 factorial? Isn't that just 1? Look, 3 factorial. What is 0 factorial? 1, right, by definition. And then 3 minus 0 is 3. So this is 3 factorial over 3 factorial. X to the 0 power is 1. And then over here,
So
we get,
rectifies to 1.
yep, that rectifies to be a 1. So all of that's going to be a 1 plus. Now here, this is going to turn out to be, I'll do it like this, 3 times 2 times 1 on top. On the bottom, 1 factorial is 1. 3 minus 1 is 2. So 2 factorial on the bottom is 2 times 1, x. Then 3 times 2 times 1 over 2 factorial is 2 times 1. And then 3 minus 2 is 1. So times 1 factorial, which is 1. I know I'm going fast here. Last one is 3 factorial over 3 factorial times 0 factorial, which is 1. So you get 1 plus, let's see, the 2's and 1's cancel, 3x plus 2's cancel, 1's cancel, you get 3x squared plus 3's, 2's, 1's cancel, you just get x cubed. That is the binomial expansion of x plus 1 to the third power. Now, you would never want to do a binomial expansion using a power series if you're only doing the third power, because this third power is easier to do by hand, right? Right? But what if you wanted to do x plus 1 to the 90th power? Right? What if you wanted to? Well, that's going to be a bunch of crap in here, right? And wow, I mean, you sure as heck probably don't want to expand that by hand, but what you could do is start building it out with the series.
Still gonna suck with the series.
It would suck with the series, but it would be doable. Like, it would be doable. It would be arithmetic, right? Factorial stuff is all it would be. You wouldn't be doing all this distribution and keeping track of all this other stuff. It would just be the series. Let me show you something else. If I try this, and I know in my Cal 1 class, I probably did this. So if this looks familiar, it's because I did it in Cal 1. If I ask you to take x plus 1 to the 0th power, that should be equal to 1, right? Everyone agree that that's 1. If I do x plus 1 to the first power, that's x plus 1. If I tell you to do x plus 1 squared, that's x squared plus 2x plus 1, right? If you were to square out x plus 1. If I tell you to do x plus 1 cubed, this would be x cubed plus 3x squared plus 3x plus 1. We just did that by hand, right? So I know my Cal 1, you remember me talking about this? This is called Pascal's triangle, or this builds out what's called Pascal's triangle. There's a pattern here. If I go to x plus 1 to the 4th, then what's happening here on all of these is that as you move from left to right, the powers on x go down. So I should have an x to the 4th. I should have some number in front of x cubed. I should have some number in front of x squared. I should have some number in front of x, and then I should have some number by itself. Right? That's the idea of Pascal's triangle. The question is, what are these numbers? And you're taught that in Pascal's triangle, the two end numbers are always 1s. And then this number comes from adding up the previous two coefficients. 1 and 3 gives you 4. 3 and 3 gives you 6. And 3 and 1 gives you 4. If you haven't seen it, I'm not trying to teach you Pascal's triangle or go through. I don't want to spend a lot of time on it. The beauty of Pascal's triangle is that you can build the next row easily by just knowing what the previous numbers are. Like, I know the next one will be 1 x to the 5th plus, now I add these two numbers together, you get 5 x to the 4th. Then I add these two numbers together, 10x cubed. Then these two numbers together, I get another 10x squared. Then these two numbers together, I get a 5x, and then my last number is 1. That's what x plus 1 to the 5th power would be if you multiplied it all out. The drawback to this, okay, the drawback to this is that if I wanted to know what x plus 1 to the 20th power is, you've got to build out the table now, right? You've got to build out Pascal's triangle. Not with the series though, because look, these numbers, believe it or not, these numbers were actually that k choose n. This right here is 5 choose nothing. This number here is 5 choose 1. This number here is 5 choose 2. This number here is 5 choose divided. 5 choose 3. This number here is 5 choose 4. And the last one is 5 choose 5. Right? If I give you 5 objects and tell you to take none of them, there's only one way to do that. You take nothing. If I give you 5 objects and I tell you to take one of them, there's 5 different ways you could do that, right? If I give you 5 objects, tell you to take 2, there's 10 ways you could do that. We actually did that by hand. If I tell you to take 5 objects, take 3, there's 10 ways to do that. 5 objects, take 4, there's 5 ways to do that. 5 objects, take 5, there's only 1 way to do that. So that means that this, even though I don't have to build out the table, I know the first number in front is 20 choose none, x to the 0, which is, yeah, I'll put x to the 0. Plus, the next one will be 20 choose 1, x, then it'll be 20 choose 2, x squared, 20 choose 3, x cubed, plus dot, 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 all the way till I get down to 20 choose 20, x to the 20th power. That is the binomial expansion theorem, basically. Like, we have a way of expanding any binomial using this, but it is developed from the idea of the Maclaurin series.
That's interesting how 5 choose 2 and 5 choose 3 are the same.
Yeah, they are. It is weird, but it happens, right? Happens to be that. All right. So if you go now and let's say we were to go to, I don't know, let's go to Google and let's just type in binomial coefficient formula. No, let's just do binomial expansion. Yeah, you see, I mean, now if you do x plus y to the n, there's some differences in the formula, but do you see this n choose k? They have it backwards. It looks confusing because it's backwards. Ours was k on top, n on the bottom, and that's because they're using k for their index on their sum. We used n for our index, and they used n as their power. We used k. So it looks backwards, but what I'm getting at is that parentheses with the 2 numbers, n and k in it now, that should have some meaning to you now. All right. That's what gives you the coefficients of the expansion. Where did that formula come from? Where did it come from? Where did that whole idea come from? It came from building out a table and realizing what the successive derivatives would give you, and then making this very nice connection that if we define this to be this, that these two are equivalent. All right. We're done with that? Is that okay? Let's continue. I'm gonna run out of time. Example 8. I really want to get to the end of this today. All right, so now we're actually going to do some integration. All right, so we know everything we've learned, okay? Everything we've learned about series, let's just kind of have that on the side right now. And now we're back earlier in the semester, and I ask you to find the antiderivative of e to the negative x squared. Okay, I'm asking you to find that. And so you go through, you're like, basic U sub, integration by parts, all these different techniques we learned. Nothing is going to work. Nothing's going to work. I'll convince you by going to Wolfram, and I'm going to have it do the antiderivative of e raised to the negative x squared. And what it's going to give me is some weird function you've never heard of, right? It's going to give me 1/2 times the square root of pi erf x. And erf x is what we call an error function, which is beyond the scope of this class. Okay, this is where they get into the error function. It's basically, we don't have a way of finding the antiderivative, all right? Go to Symbolab, you're not gonna be able to find the antiderivative. But what we can do now is we can approximate the antiderivative with a power series. So what I'm gonna do first is I'm going to take e to the negative x squared, and I'm going to use the Maclaurin series for this. All right, I'm gonna use the Maclaurin series. Now, we know that Maclaurin series, if you give me e to the x, just e to the x, it's sum n equals 0 to infinity of 1 over n factorial x to the n, right? That we established it's on our sheet. It's on our little cheat sheet that I just showed you, right? We know that's what that e to the x is. So if we want to know what e to the negative x squared is, all we're going to do is replace the x's in this formula with negative x squared. So it's going to become sum n equals 0 to infinity, 1 over n factorial, negative x squared to the n. That is the power series, or the Maclaurin series, for e to the negative x squared. So if I'm trying to do this integral, I'm now going to do the integral of this series. Right, dx. And I'm going to do it by writing out the terms. Let's write out some of the terms of this. Before we do the antiderivative, let's let n be 0, then 1, then 2, then 3. So if n is 0, we should get 1. What about if n is 1? 1 over 1. Negative x squared to the first power is just negative x squared, right? So minus x squared. What would happen if I plug in 2? We're going to get a plus 1 over 2. I'll put factorial, even though 2 factorial is 2. I'll put 2 factorial. When I square this, that's why it was positive, right? Because when I square this, it gets positive. And when you square the squared, you get x to the 4th. So I plugged in 0, 1, 2. Now I'm going to plug in 3. This should be a minus 1 over 3 factorial. It's a minus because when I take negative x squared and cube it, the negative 1, times negative 1 times negative 1 gives you minus. And it'll be x to what power?
The 6th?
6th. Let's go one more. It'll be positive 1 over 4 factorial, x to the 8th. And it keeps going, right? Dot, dot, dot. Let's integrate that. X minus 1/3 x cubed. Just for the sake of doing it, this number is a 2. This number is a 6. This number is a 24. So I took the antiderivative of 1 and got x. Took the antiderivative of x squared, got negative 1/3 x cubed. Now I'm taking the antiderivative of this. So I should get a 1/10 x to the 5th, right? Because I have to bring a 1/5 out front that hits the 1/2. Minus here, I'm going to get a 7 on the power and a 1/7 out front. So 1 over 42 x to the 7th. And then I need to do what? 24 times 9, right? Plus 1 over 216. Are y'all seeing where these numbers are coming from? Do you have any questions about those? You're all okay? So that's the general antiderivative, right? With a C in front, because it is the the indefinite integral. So I put a C out front. There it is. You wanted to know what the antiderivative of this was? I just gave it to you, right? If I go back to Wolfram, if I scroll down, it does give me the series version of the antiderivative, which is exactly what we got. X minus x cubed over 3 plus x to the 5th over 10, right? It gave us at least the first 3 terms. So now I can answer part B, because for part B, we have a definite integral. And so I want to know the definite integral here correct to 4 decimal places. So all I do to do this part is I take my antiderivative, right? I take this antiderivative that I just got. I can ignore the C. because when you do a definite integral, the c goes away. I'm going to take that and I'm going to evaluate it 0 and 1, right? Well, good news. When we plug in 0, all this goes away, right? So we just need to plug in 1. So this is 1 minus a third plus a tenth minus 1 over 42 plus 1 over 216, right? And then this goes on and on. How do I know I'm correct to 4 decimal places though, right? Isn't that what I wanted, 4 decimal places? Well, I can start looking at these numbers. This is 1 minus 0.333 repeated plus 0.1. Let's see, 1 over 42 is minus 0.0238 plus, I'm rounding there, 1 divided by 216. This is 0.0046, right? Notice these numbers are getting smaller, right? I need to go out far enough so that I have zeros in the first 4 decimal places. I haven't gone out far enough, have I? I need to go further, which means I need to know what this pattern is and keep going backwards with it. How far do we have to go? I don't know. Do you get the idea? Let's just change the problem to 2 decimal places, all right? And then I'm done, because look, when I got to this term, I had zeros right here. So I know my next term is not going to change the first 2 decimal places. So whatever this is, add this up on your calculator. Let's see, 1 minus a third plus a tenth minus 1/42 plus 1 over 216. I get approximately 0.74748, something like that. And I know that this is correct to the first 2 decimal places. Let's see, if I want it more accurate, I just go out further. And I've got an infinite series to go. I can go as far out as I ever need to go.
Couldn't we also find what the series is of this? Like the not the all spread out, but like the little summary thing at the beginning?
Like a summation?
Yeah, our summation.
Absolutely. Yeah. You could write it as a series with sigma notation as well.
Yeah. Okay. Because I was gonna say, because like this is a it's the answer and it's correct, but it's also like an awful thing to look at, and you're not going to go writing that, you know,
But what
as an answer to a question. You know what I mean?
Sure.
So
What
like,
tool, go ahead.
I was just saying, like, it seems to me that being able to express that sigma notation seems like it's more useful for the sake of actually answering a question. Is all.
Yeah. What I think you need to keep in mind, golly, what the hell? I think what you need to keep in mind here is that the beauty of the series is that it just turns into arithmetic, right? It just turns into adding and subtracting powers of numbers and multiplication and division, right? Which we have a tool that's really good at that, called a computer, right? A computer will take this out really far in a split second. Like, we aren't going to want to write this out, right? But we're going to want to write out, we're going to want to code up into a program, an algorithm to do this, right? We can define the series in their code and then have it do a do loop or something, or a for loop for a certain amount of time and compute this for us, right? That's the whole idea, is this is using the computer to do our arithmetic. But getting the series, that's the part we have to do. So not to lose sight of what we just did, we found the area underneath that curve, right? Here's the graph of e to the negative x squared. There's the whole graph. If I just look at it between that doesn't change anything. If I look at it just between 0 and 1, what we did is we calculated the area underneath this curve to be approximately 0.74, whatever it was, right? We know that what that area is. Okay. Okay. We have ways now, in theory, we have ways of finding the antiderivative of any function so long as we can convert it to its power series. Converting a function to its power series is either using our table to cheat or creating the derivative list and creating the formula for it. But in theory, we have ways of doing stuff that would be nearly impossible to do, if not impossible, by hand. All right, you all right? We've got time here. I want to share something with you. We're going to shift gears here. I'm going to play a video for you. So have your mics turned up or your speakers turned up, not too loud, where you can hear this. I'm going to take you through this, all right? Go full screen. Okay, where's my play button? Can't see my play button.
Going on.
Oh,
It's
there we go.
going on. It seems that you are not happy. You are not happy with the series.
I'm going to go back. It's hard to understand what's going on, so I'm going to translate. Okay, I will translate.
Going on. It seems that you are not happy.
It seems that you are not happy. Laughing.
You are not happy with the series.
You're not happy with the series. Okay.
How you multiply the series. But
How you multiply the series.
let's see now some other example. What I can do. Yeah.
On there, from that first line, how did you get from the first line to the second line?
You multiply.
So there's a student saying, how do you get from that line to the next line? And the teacher says, you multiply. All right, so let me keep playing. There's a lot of laughing.
Show exactly how.
Student says, can you show us exactly how to do it?
Well, exactly how? Let's see.
What, the camera's going to move, don't worry. You'll see what they're talking about in a second. Right there, that's a Bessel function, right? As a Bessel function, we talked about this capital J, that's the series for the Bessel function. I'm guessing this is probably a differential equations class. It is, there's a differential equation right there. That is a separable differential equation, second order, second derivative. Yeah, so this is like probably a differential equations class, maybe some sort of engineering, like analysis sort of course where you've got differential equations in the class. Okay, so there's students, they're asking him about something. He's looking in his notes. Here we go.
From here to here.
Yes.
Oh, you can divide one.
Okay, so he's saying from here to here, right? The students are asking about from here to here, going from here to here, how it's done. And he just answered, you just divide one. Okay, that's what he said.
No, that doesn't work.
Students saying, no, that doesn't work. That doesn't work.
Why not?
Can you do it manually? It doesn't work. It doesn't make any sense.
You hear the student? Can you do it manually? Because it doesn't make any sense.
Okay, let's go further.
Why are you ignoring my question? That
No,
doesn't make any sense.
you are doing this.
You don't answer anybody's questions.
Okay, let's go continue. So
That's the end of the video.
it seems that you are not.
So you know, I've shown this video to my Cal 2 classes like every single semester, right? Because there's a lot to be learned in this. You can look at this from different perspectives, right? From the student perspective, I think the teacher could have done a better job of explaining what the hell the student was trying to understand. I get that. The student did not understand how to get from here to here. He asked, how do you do it? The teacher answered him, you divide 1. Okay, you take this number 1 and you divide this into 1. That is the answer to the question. How did you do it? I divided 1. The student didn't know how to do that and told the instructor that it was wrong, that it doesn't work. Okay, that's the student not knowing how to do something. That is a prerequisite topic to the class. This is a differential equations class. The professor is going to assume that a student has seen how to take the number 1 and divide it by an infinite series. How do you do that? So the teacher, I think, is kind of like, wait, come on, you're just messing with me, kind of, you know, like this is arithmetic. It's arithmetic. I think that's the way he's thinking as the professor. I'm not defending him. He could have done better. The student could have definitely done better. But it just goes to illustrate that when you're sitting in a class and you don't know how to get from one step to the next, you need to take the time to figure that step out, especially if your teacher's giving you the indication that that's something you should have known coming in, right? He's teaching something completely different right now. I mean, like he's in the middle of a problem and it's just one line that he's jumping from one to the next. So he's obviously thinking this is something the student should know how to do. He doesn't have time to do it. Like we're about to do this problem, okay? We're about to do it. But if he sat there and had to do this by hand in class, you wouldn't get to anything else, right? I mean, he would take too much time. So the next topic for us is multiplication and division of power series. How do you take a power series and multiply it or divide it by another power series or by anything, right? So we're going to do this first one here. We're going to find the first 3 non-zero terms of this Maclaurin series. So disappointed. Okay, so I'm going to try this. Here we go. I'm going to try and find the first 3 non-zero terms of this. E to the x times sine x. So what I'm going to do is I'm going to first write out what is e to the x as a series. 1 plus x plus 1/2 x squared plus 1 over 6 x cubed plus 1 over 24 x to the 4th plus ... forever, right? That's e to the x. How do I know? We've already talked about this three times today. E to the x, that is the Maclaurin series for it. Now, I didn't write the factorials. I just put 2 factorials, 2, 3 factorials, 6, 4 factorials, 24, right? Now I need to multiply that times sine of x. But I need sine of x written as its series, as its Maclaurin. So let's pull up the table real quick. Sine x, I'm going to write it with this one right here. X minus x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial. That's the one I'm going to write. I'm not going to write it in this form with the sigma. So it's x minus x cubed over 3 factorial. That's 1/6 x cubed. The next one is plus 1 over 5 factorial. What's 5 factorial? Should be 120, 120. So 1 over 120 x to the 5th minus 1 over, I need 7 factorial. I need 7 factorial. I don't have it memorized, sorry. 7 times 6 times 5 times 4 times 3.
5,040.
Yeah, 50, 40. I should have known that. Plus ... Okay. I want to multiply these two together. So I'm going to do the good old fashioned FOIL. Not FOIL, expanding. 1 times that, 1 times that, 1 times that, 1 times that, right? And when I do that, let me write out what I get. First, I get an x. Then I'm going to have a minus 16x cubed, right? Watch the way I write this. I'm going to leave a gap in the middle. I left a gap in the middle because on my next multiplication, I might get an x squared and I need somewhere to put it. So I'm leaving a gap between x and x cubed. Do my next multiplication, I have a plus 1 over 120 x to the 5th. And then I have a minus 1 over 50, 40 x to the 7th. Are y'all good with that? I can't go forever. I've got to stop somewhere. So I'm going to just stop there. Now I'm going to move to the x and multiply the x through. Right? And when I do that, the first multiplication, I get x squared, right? I'm going to put that right underneath here, x squared. And then when I do the second multiplication, I get negative 1/6 x to the 4th. It's basically all of these, but the power is going up, right? On each of those. So plus 120 x to the 6th. And then there will be another one out there. I'm just going to say plus ... Because the question asks for the first 3 non-zero terms. I only want the first 3. So far, I've got an x, I've got an x squared and an x cubed here. Let's do the next multiplication. I'm gonna do this in brown. This times this, this times this, this times this. This is going to start looking ugly. 1/2 x squared times x is 1/2 x cubed. Put that here. Notice I lined it up with the x cubed here. 1/2 x squared times negative 1/6 x to the 3rd. That'll be a negative, what, 1/12 x to the 5th. Do y'all agree that's the second multiplication? This one times that one. I'm going to stop here because I only need the first 3 terms. An x squared, and x cubed. I just got to make sure I'm not going to get any more of these guys. So let me do this multiplication, this one through to here. What's that going to give me?
1/6 to the 4th.
So I'm going to get a 1/6 to the 4th, and then there's going to be more stuff, right? But after that, I'm not going to get anything else, right? There's going to be nothing else that I'm going to get, right? I'm not going to get anything else that's going to be under a power of 4. So I have my first 3 terms. I just need to add these up. So I add down, I get x. This, I get x squared. And then when I add those together, I have to add the coefficients. So negative 1/6 plus 1/2, right? I have to add fractions here. Oh
That's
gosh.
a third, isn't it?
Yeah, you're going to get what, negative 2, 4, 6. So negative or positive 1/3, right? Positive 1/3 x cubed plus ... What we have done here is we have multiplied 2 series together. And we've only got the first 3 terms. You can imagine that if I asked you for the first 8 terms, this would be a mess, wouldn't it? But it really is just mechanically, it's just distribution. That's all it is. Expansion of infinite polynomials. All right. Let's do the next one.
Sir, real quick, is that the only method of doing it? Is there like another way of doing it?
That's pretty much it. Yeah.
Gotcha. Nice. I like it.
Yeah. So what's cool about this is this. If I wanted to integrate e to the x sine x now, right? If I wanted to integrate that, I could just really integrate x plus x squared plus 1/3 x cubed, right? And that would be kind of an approximation. The further I go out, it would be exact, but I wouldn't have to do integration by parts or anything like that, especially if you gave me some limits of integration, right? 0 to 1, man, then I'm ready to roll because I don't mind plugging 0 and 1 into this, right? So it makes it better. Okay, let's look at the next one. let's not do tangent. I want to do something else because I want you to see what the professor was talking about in that video. I want us to find first 3 non-zero terms for f of x equals secant x. Secant x. All right, well, the only thing we know about secant is that secant is 1 over cosine, right?
So would we divide 1 by our cosine?
Yep, we're going to
Series.
take 1 and we're going to divide it by the power series for cosine. Power series for cosine is 1 minus 1 over 2x squared plus 1 over 24x to the 4th minus 6 factorial 520. Hold on, I just want to make sure I don't screw this up. Yeah, 720. Okay,
720.
1 over 720 x to the 6th. Do y'all understand the denominator is just the Maclaurin series for cosine? Now look, I mean, I'm taking the number 1, right? And I'm going to try and divide it by this series, which is exactly what this professor was doing right here. He took that. Now it's not the same series, okay? The denominator here is not cosine, right? That's not cosine, but it's the same principle. Taking 1 and dividing by this series. This x cube, this is an x cube, it's hard to see. That just comes down, okay? That just came down, and this became this, okay? And that's what the student was saying. That doesn't make any sense, all right?
I'm just relieved that this isn't something we were supposed to already know.
Yeah.
Because I was sitting there staring at it in that video going, I don't know how to do that. So
But now that you'll see it, it's not that bad. I mean, well, I don't think it's that bad. Let's see. I'm going to take the number 1 and I'm going to divide it by this series, right? That's what this means. I'm going to have to do long division, right? So I start with the very first term. I need to turn 1 into 1, right? So what do I multiply by? 1. So I put a 1 here. And now I multiply 1 times this entire thing. So I put a 1 here. Now 1 times that is going to give me negative 1/2 x squared. Notice I left a space in case I get an x term to come out somewhere. 1 times this, I get a plus 1 over 24 x to the 4th. And then I'll have a minus 1 over 720 x to the 6th. And that keeps going, right? Then how did division work? Long division, you come through and now don't you subtract this row? Right? You subtract that row now. So it changes the signs. This becomes minus, plus, minus, plus. And now add down. You get 1/2 x squared minus 1 over 24 x to the 4th plus 1 over 720. Does anyone have a question on what I'm doing right now? We continue to play the game. You need to turn 1 now into 1/2 x squared. So I'm going to multiply by 1/2 x squared. And let's do it. I multiply that times 1/2 x squared. I get 1/2 x squared. Be careful on the next multiplication. Here times here. What do I get? Negative 1/4 x to the 4th. I'm going to line it up right here. Negative 1/4 x to the 4th, right? The next multiplication, I'm going to get positive 1 over 48 x to the 6th. Positive 1 over 48 x to the 6th. I lined it up underneath the x to the 6th. That's good enough for now. Let me keep going. Subtract this, which changes the signs. Come down again, right? These go away. Oh, crap. I need a common denominator here. So negative 1 over 24 plus 1 over 4. Common denominator is 24. 6. That should be 5 over 24 x to the 4th. You could do that with enough time, right? You could figure that out. This is the same as 6 over 24. Right? Okay, I'm not even gonna do the next one. I'm not gonna do the next one because I only need the first 3 terms. So whatever this turns out to be, I know what I need to do now, right? I need to turn 1 into this. So that'll be up here, plus 5 over 24, x to the 4th. And then I know there's more, okay? But I've got the first 3 terms, don't I? The first 3 non-zero terms. Y'all good? Y'all good? Y'all good? Y'all good? You don't like it, Eduardo? No. Somewhere on my YouTube channel, I have a video that is me working this particular problem out. This one. I'll try and find it. I'll send you the link. So I tried my best to interpret what it says. I'm pretty sure I interpreted it right because I got the same thing he got here. And if you read the comments, it's funny, you know, because it's like, you know, people pay way too much for an education to have a professor not answer the question and all this. And then there's other people who are like, hey, it's simple freaking arithmetic. You should learn your math before you know, I mean, so it's like both sides. I'm in the middle on this one. Okay.
Both people could have done a lot better.
Exactly. Yeah. Okay. I really only have 8 minutes. I really want to try and show you all this. I really would like to show you, if you'll allow me the time, I'd like to show you that this equation e to the I pi plus 1 equals 0 is.
This is what I've been waiting for.
What you've been waiting for? Okay, I'd like to show this to you. If you need to leave at 12:40, leave. You're not going to hurt my feelings. This will be on video. You can come back and watch it.
Is that I like irrational pi?
That is I, the imaginary number. So first, let's talk about why this equation is considered to be the most beautiful equation in math. Not by me. Beauty is subjective, okay? But a lot of people say this is like one of the most elegant equations. And the reason is because it contains all of the most important numbers in math that we use. So let me explain why these numbers are important. 0 is an important number because in our number system, it is called the additive identity. Now that may be like, okay, big deal. It's called the additive identity. Lewis, one of your classmates, and I were getting into this the other day, that when you talk about the number system, our number system is what's called a field. And a field is basically a structure that we have on our number system. And one of the things that's required to have a field is all fields must have an additive identity. They all have to have an additive identity. And 0 is the additive identity for our number system. 1 is what we call the multiplicative identity. And I guess I should point out why we call it additive identity. If I take any number and add 0, it doesn't change the number, right? 4 plus 0 is still 4. X plus 0 is still X. Every field must have that. A field must also have a multiplicative identity, which means that it must have a number you can multiply by that doesn't change anything. So 4 times 1 is 4, right? X times 1 is X. So those two numbers are used, very important. They're part of our field. Okay, we've got pi. We all know pi. It, you know, circumference, circle, diameter. It's all beautiful number. We use it all the time. We've got e. E was the base of the exponential function that grew in a way that it's its own derivative. Like it's the only function that is its own derivative. So e is that very special base. Like these are important. And then of course I is the imaginary number. I is the square root of -1, right? And then we stayed away from that. We have stayed away from the imaginary number this entire class. In fact, the entire book, Calculus 1, 2, and 3, you do not touch I, okay? After you get through calculus, you can take a class called complex variables where you bring I into the game, all right? So
it's
before I can show you that,
post-calculus before you get to deal with that effectively.
you need 4 dimensions to understand I. And so, well, yeah, it's not something that's easy to visualize.
Yeah, I imagine.
Okay, so before I continue and I show you this, I want to explain the property of I. I raised to the first power, oh, not derivative. I to the first power is just itself I, okay? I squared, I times I is the square root of -1 times square root of -1, which is equal to 1. I'm sorry, -1. That is the big property of I. It's the number that when you square it, you get -1. So I squared is -1. I cubed is basically I times I squared, right? That's true. I cubed would be I times I squared. And I squared is -1. So this just turns out to be -I. And then if I do I to the 4th power, you could look at that as being I squared times I squared. That's -1 times -1, which is 1. I to the 5th power would be I to the 4th times I, which is 1 times I, right? Because I to the 4th was 1, and that's just I. So aren't we back where we started? We've completed a cycle. We started with I to the 1st. We went through 2nd power, 3rd power, 4th. Now we're back to I, which means that if we have I to the 1st or the 5th or the 9th or the 14th, it should be I. If we have squared or 6th power or 10th power, it should be -1. Am I making sense? This is going to keep cycling through. Okay, I'll come back to this if I need to. I'm ready to do this. Y'all ready? I want to show, all I have to show is that e to the I pi is equal to -1. Would you agree? If I'm telling you that this is true, then I can just move the 1 to the other side. So if I can show you that e to the I pi is equal to -1, would you be satisfied? Yes? Okay. Yeah, I hope so. Here we go. I'm going to do it. I'm going to start with this side. I'm going to show it's equal to -1. Here we go. E to the I pi is equal to 1 plus I pi plus 1/2 I pi squared plus 1/, sorry, I'm going to do factorials. 1/2 factorial, 3 factorial, I pi to the 3rd plus 1/4 factorial, I pi to the 4th plus 1/5 factorial. I need to go out a little bit for you to see this. I pi to the 5th. You all know what I'm doing here? What am I doing?
Preparing to make a series.
I'm plugging it into the Maclaurin series, right? This
Yeah,
is the
it's a
Maclaurin
Maclaurin
series for e to the power x, but I'm replacing all the x's with I pi's. Right? Believable? But okay. Now, this is 1 plus I pi plus 1/2 factorial. Tell me what happens here. Tell me what happens here. If I square the I and square the pi, what happens when I square the I? What is I squared?
-1.
-1.
-1. So I'm going to make this plus a minus. Is that all right? And there's no more I because I squared is -1, but I still have pi squared, don't I? Now I have plus, I think it's plus 1/3 factorial. Okay, what's I cubed?
-I.
Negative I. So I'm going to put the negative out here, right? I'm going to put the I here, and then I'm going to have pi to the 3rd power. So I cubed the I, that gave me -I. I pulled the negative out front, I put the I here, and I cubed the pi. Still good? Plus 1/4 factorial. Okay, I to the 4th power. What was I to the 4th power? It was 1. So we just get pi to the 4th, don't we? Okay, next one. I'm going to have 1/5 factorial. What is I to the 5th?
I.
It's just I, right? So it's going to be plus, and I'm going to have I, and now I'm going to have pi to the 5th. I'm going to keep going. Next one is going to be, what is I to the 6th power?
-1.
-1 again?
Yeah, so we would be a 1, 2, 3, 4. This is basically back 5, 6. So we're going to be back at -1. So I'm going to make this a negative 1/6 factorial. It's -1, so I don't have an I anymore. Pi to the 6th. I need about 5 more minutes. I'm going to go another one. What would happen if I did the 7th one? 7 factorial. What would I to the 7th be? So this is 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. It would be negative I,
Yeah,
wouldn't it?
negative I again.
Negative I. So I'm going to have this be a negative. And now I have an I, but now it's pi to the 7th. Let's see if that's enough for us. Let's see if that's enough. Okay. All right. What the hell am I doing? I'm now going to look at everything that has an I in it. I. Those all have I's. Everything else doesn't have I, right? So I'm going to rearrange things. Let's do the things without the I's first. 1 minus 1/2 factorial pi squared plus 1/4 factorial pi to the 4th minus 1/6 factorial pi to the 6th, right? Those are all the things without I's. And I would have more of these, wouldn't I? There would be more out here. I'm just going to say plus dot, dot, dot. That's the first group. That's the group in blue. Plus, now let's do the group in yellow. All of these have I's, right? All of them have one I. So what I'm going to do is I'm going to put an I out front, factor an I out of all the yellow ones. And now I have pi minus 1/3 or 1/3 factorial pi to the 3rd plus 1/5 factorial pi to the 5th minus 1/7 factorial pi to the 7th plus that goes forever, right? Anybody see it? Can somebody tell me what this is?
Is that cosine?
That is cosine of what?
Pi,
Cosine
isn't
of
it?
x. It's cosine of what?
Pi, right?
It's cosine of pi. That's the cosine series with pi plugged in.
Is the other one sine?
Plus I, and then this one is all the odd powers. This is I times sine of pi. Cosine of pi is -1. And then I times sine of pi is 0. And so your answer is -1.
That's crazy.
That's cool.
That's awesome.
That is cool.
Yeah, that's really cool.
I'm gonna show my mom.
Yeah. So, yeah, sorry I had to rush through that, but you saw it now. So, all right, final exam. I know we're way out of time, but the final exam, you know, I would just look at those 2 reviews that I went over or that I sent out. I will tell you that the test is going to be mostly chapter 8. Okay, mostly chapter 8, but there is going to be at least one problem on there where you're gonna have to do a volume with a solid where you rotate around the x-axis. Okay, and I'll give you more of a hint on it. It's going to require integration by parts. Okay, it's not a problem I get to choose. It's a problem we have to give you. So that's about all I'm going to tell you on it. Don't be scared of it. It's integration by parts. You'll be okay. But otherwise, I would just look at these reviews and except for the 9.1 and 9.12, 9.1, 9.2, 9.3, 9.4, I will put problems on the test from this, but they will be bonus and bonus only. And so if you're interested in that, go to my YouTube channel, go to my Calculus 2 internet lectures. And where's my standard screen? Down here on the bottom, I have 4 videos. It's about a total of 3 hours of video if you're interested in those bonus questions. And in the future, if you get into another, class and you're talking about parametric and polar and you want to have something to look at, it's there. All right. Okay, I'm sorry to go so long. I really want to get through that stuff, but keep your eyes on your email. If for a study group, maybe on Saturday, and please reach out if you need help. Any questions?
Sir, how much weight have you lost since your weight loss?
You want to take a guess?
Let's see.
1
Hard to tell
million
over
pounds.
camera, right? It's hard to tell over camera, I guess, huh?
It's 1 million pounds. I saw him.
I'm gonna say
50.
above 10.
Can't say it's not
Over
statistically
10
likely.
pounds.
I'm gonna say 20.
20?
No. He looks like somebody that weighs 175 lean.
Oh, good guess. Here it is. This is my weight today. 179.6 is my weight today. My goal is 174. I like to be at 174. But look where I started.
Sir, I love it.
214. I was 214 pounds at the beginning of this semester. I've lost 34.6 pounds.
You were just gaining, sir. You were
Hell
just gaining.
yeah.
Yeah.
So
So
I like this graph. So much.
Congratulations.
I love-
This is the
I love
most
way you track
Giovanni
this.
thing I've ever seen in my life.
Yeah, no, all right.
notice at the end, the last week, I have not worked out. I've taken a week off. I'm eating right, but I'm just not working out as hard because I just wanted to take a week off. And you can see I kind of like flattened out. But my goal is to hit the 174 by the 28th of May. That's my goal.
Is this the most beautiful graph in mathematics?
To me, it is. To me, it is right now.
I think that's e to the I pi. Dude.
Yeah, no, that's a lot of weight. That's a lot of weight to lose in 1, 2, 3, 4. Well, I have the days here. Today is day 86. So on average, I've lost 0.4 pounds a day. 0.4 pounds.
You're bicycling, right?
Mm-mm.
No, just like running?
Nope, I'm doing everything at home. I've got, I started with some videos that are just like 30-minute mixture of just like cardio and strength, just dumbbells and stuff, just to get myself going. And then I have an elliptical and I have a rower. So I'm doing about, well, you can see, I know this is way too much data. You can see here all the ones, I'll make this bigger. All the ones represent days I've taken off. But the red here is how many calories I burn that day in exercise. So my average is 578 calories a day burned through exercise. And then this is my intake. I've averaged eating 1,400 calories a day because I'm keeping track of my input. So I've got my calories are way down, like what I'm eating, and my exercise is up. I mean, that's the only way you can drop almost half a pound a day. I mean,
Yeah.
It's almost not even healthy to go that extreme.
It's
Especially
cutting
like if you're
season.
like really overweight, you can lose more than half a pound a day. But you plateau, you get to a point like when you're in a healthy weight, it's actually not good for you to lose that much weight because your body starts to absorb your muscles, right? It's like,
But I
okay,
get like-
energy, I'll just go to the muscle and take the muscle.
I get
So,
like 5 points extra, right? That was a pretty good guess.
yeah, pretty good. Yeah, I get a little bit obsessive when it comes to data, as you can tell, but I got to keep track of things. I also have a chart here that shows when I work out what my heart rate zones are. So like whatever my heart rate is, because I have a heart rate tracker, right? That's keeping track while I'm working out. So if I look down and my heart rate's 140, I know that I'm burning 14 calories a minute that way. And then I have how much time it'll take me to burn 300, 200, and 100 calories. So it just kind of keeps me, I have a chart next to my machine. So I'm sitting there, I'm like, okay.
That's absolutely insane.
Yeah, it
Sir,
is insane.
Are you familiar with the Garmin?
With what?
The Garmin watches, Garmin products?
Yeah. Uh-huh.
I have their watch and their heart rate monitor, and I've tried doing a graph on them like on Excel, but I just much
Yeah.
rather use what they have online. That's cool. It's awesome.
No, yeah, the Garmin, so the Garmin, I have a thing called the Edge, which is made by a company called Yahoo. No, wait,
It's-
Yahoo?
Yeah.
It's a cycling computer. It's actually a cycling computer, but I use it as my heart rate monitor because I can just have it next to me. And I have a chest strap, right, for my heart rate, because the wrist ones, they're not that accurate, right? So I have the chest one. And so that's where I get my calorie burn from. And yeah, when I'm cycling, I use like a Garmin to track my route. But I'm trying to do everything at home because I just don't have the time to go hit the trail. It takes me 30 minutes, 45 minutes to get there, unpack my bike. It's just not convenient. Here, boom. Like after I'm done with y'all, 110, I'm gonna go work out for an hour, and I've been doing that every day of this semester pretty much. So
Hi, Professor.
Yeah.
I know this is one of the last classes that we'll have, and I just want to go ahead and say, man, I do appreciate the